Okay, so we're going to start with our recap of pressure and go over fluid statics and hydrostatic forces on submerged systems in this lecture and the next lecture. The first thing we're going to do is start the lecture with the recap of Chapter 3. So there's some really important principles that we've learned so far. The first principle that we've reviewed is that pressure is equal to force over area. Very important. Now, when we're talking about the submerged object, that principle is going to be very, very, very important. Okay? We also learned about pressure as it increases, right? P increases as we go deeper underwater, right? That principle is also very important. The relationship to calculate that pressure distribution is pressure is equal to negative gamma Z. We typically use this equation when we're discussing the change in pressure, which is delta P is equal to negative gamma delta Z. Okay, so these are the most important concepts that we learned from last time. And we're going to continue developing, especially when we're talking about this equation. This equation is going to be incredibly important for this lecture. Okay, so we're going to start with discussing pressure distribution. So, pressure distribution. Okay, so there are two types of pressure distributions, right? There's the easier type, which is the uniform pressure distribution. Okay, where you have something that looks like this. So you have an object. This could be what you're used to looking at would be like a beam or something with some supports, but remember this is submerged, right? So it's completely submerged underwater. So because there is no angle, so here we are flat, our theta is 0 degrees, okay? We have a uniform pressure distribution. So looks something like that. Okay, so you can see that the pressure is acting uniformly onto the object, and what you're going to end up with is what we call a pressure force, or pressure force here. Now recall that I had mentioned that pressure is equal to force over area. Okay, so that's really where we're going to get that force from. So then we can use that force is equal to pressure multiplied by area. Okay, now isn't it true that we know what the equation for pressure is, right? Acting onto a submerged being, right? That pressure is equal to gamma dz, right? Or since this is at one point, it would be gamma h, the depth of the water, okay? So this equation is rewritten then to become force is equal to gamma h A. Okay, wonderful. Now remember, this specific weight must be constant, right? Okay, so you cannot have some oil and some water. This distribution will be different, okay? So it must be constant, okay? Now, this area here is referring to what's called the cross-sectional area, okay? So this is the area that the water sees on top of this particular beam, right? So the area won't be this multiplied by this. It's going to be this face multiplied by the face into the board, okay? So it's going to look like this, okay? Think 3D, okay? And again, acting onto the face are our pressure distributions. So this is going to be your cross-sectional area, is the space here. Okay? All right. Okay. So that is for the uniform distribution, right? Easy peasy. But what happens when we have a non-uniform distribution? Okay, if we have a non-uniform distribution, things are a little bit different, okay? Right? So again, we have our water line, okay? Now, here's the bottom of the tank, let's say. Looks something like that, okay? Now, what if we have an object that actually looks like this? So it's a beam still, okay? But what did we learn about from this equation? dP is negative gamma dz. How does pressure behave? Pressure increases, right, with depth. So you're not going to have this uniform distribution, right? Your distribution is going to be increasing with depth. So it's actually going to take more of a triangular shape, okay? So this is our non-uniform distribution. We're still going to have this force due to the pressure acting onto the beam, okay? And that force is still going to be pressure multiplied by area, and it is still going to be gamma H multiplied by area, okay? Now, this is the equation. This is always going to be the equation, whether your beam is this way or it's this way. It is always going to be this equation, okay? Always, always, always. But the trick is figuring out what the heck this H is. What is H? Where is it H? Is H going to be from the top of the tank to the bottom of the beam? Is it going to be from the top of the tank to the top of the beam? Is it going to be from the top of the tank to the center of the beam? Let's get and figure out what this H is going to be. Okay. So now I'm going to draw, to the best of my abilities, this picture here. So we have, whoops, let's do blue. So we have a nice water line. We have a tank, okay? So what we're trying to do is figure out, let's say this is a gate. It's a gate. Okay, we have our pressure distribution acting onto the gate. It is increasing. I'm being kind of dramatic with these lines, but it is increasing as you go with depth, right? An increasing distribution. Now I'm going to take this gate and I'm going to move it over here. Okay, so this gate is equal to this gate. And we're going to draw some points here. So the center of the gate is usually marked with this kind of X here, and that is called the centroid. So centroid is equal to center of your gate, always. Okay, if your gate is going to be a rectangle, right, it's exactly halfway between the gate. Now, the point of interest that we are going to be looking at is called the center of pressure. Okay, is a center of pressure. This is where your force due to pressure is going to be acting on. Okay, there are some very important observations to be made here. The first observation is that, one, just kind of repeating what I said, that force due to pressure acts at center of pressure. Okay, and then two, we have that the center of pressure is always below the centroid. Always, 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 always. Okay, so you have your centroid is in the center of your object, and your center of pressure is always going to be below it. This is true for your non-uniform distribution. Remember, this is non-uniform. Okay, it's going to be true that your force is going to act somewhere below your centroid. Okay? So now we're going to start with identifying how we can calculate H and what H actually is. So let's start by kind of drawing, again, that tank perspective. So here's our top. Here's our bottom. Okay. Let's draw some, it's just to signify this is the bottom of the tank. And we have our water line. So now I'm going to draw this kind of funky bean shape. This kind of shape just represents any arbitrary submerged object. Okay, now this is going to be the face view. So this is going to be our face view. And this is going to be as if it would be like the top sheet of paper. So like the top sheet of paper. Okay. So just like any other object, you have a centroid, right? And of course, acting below it, you have some center of pressure. Now, what I'm going to do is I'm going to draw an axis, just a y-axis, through So what I'm going to do is I'm going to draw a y-axis through this object, so kind of like that, and I'm going to copy this axis, and I'm going to essentially what I'm going to do is I'm going to draw this axis kind of alongside it. Okay, so this is the face and this is the axis, but now this particular axis is going to be, so this is the same object, okay, but this is going to be the side view. So again, this is the face of your sheet of paper, and you turn your sheet of paper to the side. It's the same size, right? So this is the bottom of the object. This is the top of the object, okay? So it's the same object. Even draw another line here. So this is the object and this is the object, okay? Side view, top view. These are really important perspectives, okay? So that means that this would be the location of our centroid. So here's the centroid. Just kind of move it on up. That's the centroid. That's the centroid. And this is our center of pressure. So again, this is our CP, centroid. Okay? All right. So this is, again, going to be my y-axis. So y-axis along the object, always. This is going to be my origin. This is my 0, 0 point for my y-axis. Okay, this is the same axis. So this is 0, 0, and again, this is my y. Okay, now this is a 2D plane, so we're missing our x-axis. So the x-axis from the side view is actually into the board. So x-axis is into the board, okay, and since this is the top, the face view, right, our x-axis is actually acting in this direction. So this is my x, okay? All right, so are we together? This is my 0, 0, this is my 0, 0. This is my object, this is my object. This is my center, my centroid, this is my centroid, this is my center of pressure, this is my center of pressure. Same object, just drawn on different planes, okay? This plane perspective, the one that's the side view, is the perspective you're going to be using most of the time. But it's just important that you see where the x and y axis reside, okay? All right. So now let's start labeling some stuff. So this distance from this point, to this point, this distance is called y bar, okay? Which is, y bar is your distance from the 0, 0 plane to the centroid, okay? You have a y CP, which is this distance here, the distance from this plane to this plane, which is y CP, from here to here, okay? And that is the distance from, again, your 0, 0 to the center of pressure. Okay? Very, very important distances. Now, these distances are also here, right? The distance from here to here is also y bar, right? The distance from here to here is also YCP. So this is all the same, okay? Sorry, that's not quite straight. It's supposed to be a straight line this way, okay? So these planes are incredibly, incredibly important. Now, if we go back to our definitions, right, we have a force that's acting here, force at our center of pressure, right? That equation, force, is equal to gamma h bar A, or gamma y sine alpha A. Okay? Why is that y inside? So let's go back to our equations. So force is equal to gamma h A, but we're trying to figure out what this h is, okay? So through a series of derivations that are provided in your book, this h is actually the distance from the top surface to not the center of pressure, but actually the centroid. Okay, so this distance here, that distance is h bar. Okay, so h bar is the distance from the top of tank to the centroid. Okay, this elevation here. So that is going to be your h bar. Okay, this drawing is very, very important. Okay, it is very, very important because it identifies what elevations you need. Okay, and it kind of shows how you draw for any inanimate object. Okay, it shows you how to draw the distance from the 0, 0 plane, which is always at the water surface. Okay, always, always, always at the water surface. From the 0 plane to the centroid and to the center pressure. Okay, so we've put it all together. We have our equation. Force is equal to gamma h A. This h is h bar, or it could be called hc, where again this is distance to the centroid. Okay, so this is the equation that we're going to use. But if we go back to that picture, of course, that I erased, we have our tank. Okay, we have our side view. Okay, and we have our centroid, we have our CP, right? And we have our distance to the top, right? This is my y-axis. This is my y bar, my distance from the top to my centroid, right? Centroid. And then we have our h bar here, which is the distance from the top of the tank to the centroid. You should see me trying. This is kind of hilarious. Okay, so this equation is valid, absolutely valid. But can you also see that if you know this angle here, so this angle is your tilt angle, okay, which can be greater than or equal to 0 degrees, okay? If you know that angle, then how else can we represent this equation? Well, we know that this is going to be the hypotenuse, right? This is our right angle here. This is my hypotenuse, and then here is my opposite. So sine of alpha is h bar over y bar, okay? So that means that h bar is equal to y bar sine alpha. So we can plug that into this equation to get F is equal to gamma y bar sine alpha multiplied by the cross-sectional area. This equation is the equation for the force acting, again, where? Not at the centroid, but at the center of pressure, which is located where? Below the centroid, okay? I want to also bring up this picture because this tends to confuse students sometimes. So it is absolutely possible for you to have a situation like this where you have, so here's your water, here's your water line, okay? And we have our object. It is possible that our object actually has no tilt, okay? So here's my y-axis, okay? Again, here's my x-axis into the page, and then here's my object side view. Okay? So what is the angle here? What is alpha? Alpha is going to equal 90 degrees, right? Because this is a right angle. Okay? So we still have our pressure distribution, right, increasing with depth, acting onto the object. We still have our force here. Our force is equal to gamma h bar a, which is equal to gamma y bar sine alpha a. This is my y-axis. My h bar is still going to be the distance from the top surface to my centroid, right? So this is my h bar. And y bar is still the distance along the y-axis from the 0, 0 plane to the to the centroid. So this is still true, right? So if you plug in, right, alpha is equal to 90 degrees, then F is gamma y bar sine 90 degrees area. Well, what's sine 90 degrees? It's 1, right? 90 degrees, it's 1. So then this just becomes gamma multiplied by y bar a in this particular case because sine 90 degrees is 1, which is also equal to gamma h bar a. It is absolutely possible to have a no tilt, okay, situation. This is totally possible. Don't get tripped up. If there is an angle, use the angle, okay? If it's 90 degrees, just state it's 90 degrees and move forward. So the next thing we're going to discuss is how we determine this location, right? So this is going to be the center of pressure, and we know it is acting at YCP here, but what is YCP? And there's this is our Y center of pressure. There's also going to be an X center of pressure. And kind of what are the equations that we need to use in order to define these? So I'm not going to go over the derivation. The derivation is in your book, but essentially what you use in order to locate XCP and YCP is the parallel axis theorem, okay, is used to derive YCP and XCP. Now, the parallel axis theorem is essentially a function of your object shape. We're going to need to know the type of object we're using, that is submerged, in order to calculate your YCP and your XCP. Okay, the general equations are XCP is equal to I XYC over X bar A, okay, plus X bar. So X bar is your distance from your 0, 0 to the centroid, right, along the x-axis. Okay, so again, if you have an object where that's submerged, and here is your y-plane, and here is your x-plane, then this would be your centroid. So you're trying to figure out the distance from your 0, 0 plane to your centroid. Okay? That's your general equation for what XCP. YCP is equal to your I XC divided by your y bar A plus your y bar. Okay? I'm not skipping it. I'm going to go over it. But what are these? What are these things? So from your statics course, hopefully you learned about moments. Okay? You should have learned about moments because the I's are your second moments. Okay? With respect to an axis passing through the centroid. Okay? And parallel to either your x or y axis. Okay? So the I's are provided in your book and on Moodle. So I have this chart that shows all of the locations of centroids for various shapes. Okay? Remember, I's are a function of object shape. Okay, I'm going to give you a second to write that, and I'm going to put up the image that is going to be already on Moodle. Okay, so here are examples of the object shapes. So here we have a rectangle. Let's zoom in on the rectangle equations. So we have our x-axis, right? Remember, that's into the page, and we have a y-axis, right? That's along the side. And here is our centroid. You notice these equations require you to calculate what B is, which B corresponds to which axis? It corresponds to the x-axis here. So the x-axis, the x distance here, gives us our B length. The y-axis gives us our A length. Why do we need that? Well, in order to calculate your second moments, you need to calculate it as a function of A and B. okay? And here we have our area of a rectangle. This one's really tricky, okay? It's really, really tricky, and you need to pay very careful attention, okay? So I'm going to write this example down, okay? So here, let's say we have our water line, okay? And we have some submerged, again, gate, okay? And I want you to calculate your IXC, which is equal to 1 over 12 BA to the third. So drawing that picture again, here's your centroid. This is your x-axis, this is your y-axis, and this distance here gives you B, and this distance here gives you A. Okay? So let's say that the length here is 4 feet. Okay? And remember, this is in the x-axis is into the page. So if I wanted to draw this, again, looking at the face, it's very convenient to do both perspectives. Okay, so then let's say this distance was 5 feet. Okay, now I'm going to draw my axes. So this is my y-plane here. Again, this is also my y-plane with respect to this 0, 0 line. That would make this line my x-axis and this line my y-axis, extend that, that's my 0, 0, okay? It's my 0, 0. These two are the same, okay? They're the same. They're the same lines. This is line, and this is just x into the page, right? This is just us looking at x into the page. Okay, so now what is A and what is B? Well, B corresponds to the x-axis distance. Do you see that? This is my x-axis, this is B. A corresponds to my y-axis here. Do you see that? YA. So then what are A and B in this example? A is equal to the distance along the y-axis, which is, this is still 4 feet, right? So this is equal to 4 feet. B is going to be the distance along the x-axis, which is into the board. B is going to equal 5 feet. Do you understand? So IXC is 1 over 12 B, 5 feet, multiplied by A, which is 4 feet cubed. So the units for I are going to be length to the 4th, always. Because here we have foot cubed, so it's going to be foot multiplied by foot cubed. It's going to be, in this case, feet to the 4th power. This is always going to be the units for the moments. So now what we're going to do is a full-on problem. Work out a lot of problems with submerged gates to kind of give you a background and an idea of how to approach these problems and solve them for your homework. Okay, so I'm cheating a little bit and I'm copying and pasting a problem that I found to be very useful and interesting for students to learn. So I want you to write down the question and draw the picture on the side, and we're going to work from there. So, okay, so then again, this is what's given. This is the side view. This is our submerged item here, and we're going to draw the view off the front-facing view. So this is the first thing you're going to do. Okay. And it says a rectangular gate. So what's given is that this is rectangular. Okay. State given. Okay. Having a width of 4 feet. Okay. Is located on the sloping side of a tank as shown. Okay. So we have some angle here. The gate is hinged along its top edge. So here we have a hinge. Uh-oh. When we have a hinge, what do we have? We have a moment. Okay? It's hinged on its top edge and is held in position by a force P. So basically what's happening is the water, right, is applying some force onto the gate, right? We know what force that is. What force is this? This is our hydrostatic force. Force onto the gate. That's causing it to want to open this way, right? This is a hinge, so the hinge means it's like like a door. It wants to open this way. But there is some force at this bottom piece here, the bottom of the gate, that's causing the gate to not open, right? The beauty of hydrostatics is that it is not moving. So this is the force. So P is the anchoring force, right? So gate stays closed. All right? So friction at the hinge and the weight of the gate can be neglected. So there is no force opposing the movement at the hinge, and we're essentially saying that the weight of the gate is negligible. So let's draw our side-facing view. So here is a rectangular gate. Okay, and the width is 4 feet, so that's 4 feet into the page, right? That's our width. And this is 6 feet, right? Is this length here. Okay, so now we're going to start labeling some really important things. So let's label our distance along our y-plane. So this is my 0, 0 line. Sorry, it's my 0, 0 point. This is going to be my y-plane, right? So this, from here to here, that is my y-axis, okay? Now, if I were to draw, again, the plane from the face, you just take this point, draw your x out, and we draw our y through our object. So this is our y-plane, and this is our x-plane. Okay, so let's label some distances. The distance to the centroid is here to here, so that's our y-bar. Okay. Okay, well, what actual physical distance is that? What is y-bar? Y-bar is going to equal this distance that's given as 10 feet plus half of the gate, right? Because that's the distance to the centroid. So that's 3 feet. So this is going to be 10 plus 3 feet is the distance to our y-plane, okay? What is this alpha? Well, alpha is going to be 60 degrees, right? Because here's our match. We have 60 here. That means we have 60 here. So this is going to be 60 degrees, okay? So we're given, let's write that down. Alpha is 60 degrees. Awesome. Okay. So what we're trying to do is determine the required value at P. So we're trying to figure out what P is. Okay, so if we look at it from a free body diagram perspective, so drawing the free body diagram, okay, so here we have our gate, what do we have? We have a force, P. We have our hydrostatic force. We have our moment. Okay, so we're trying to find P. So what is true about this situation? We are hydrostatic, meaning not moving, right? So again, what is going to be our sum of moments? Well, sum of moments is going to be 0, right? Because we are not moving. We're making sure that the gate remains closed, right? Where the gate is remaining closed as long as this force is being applied, okay? So then if we do a sum of moments, and let's say we do positive this way, right? Label our positive, okay? Well then, what does our equation become? What is a moment? The moment is going to be force multiplied by the distance from that force to the location of the moment, right? So let's get another color here. So we need this distance here to get the hydrostatic force multiplied by that little distance, right? Is that going to be positive or negative? Right-hand rule. Right-hand rule states that it is going to be in the negative direction. It's going to be acting opposing this force. Sorry, this moment. So that's negative. Now what about this one? Is this promoting the moment or is it negating the moment? It's promoting the moment, so that'll be positive. So plus P multiplied by this distance. Well, what is this distance? This distance is given as 6 feet. So multiplied by 6 feet is equal to 0. Okay? So can we solve for this force? Yeah. What is this distance here? Well, this distance, right, is from this point to this point. This is little d. Okay? Now, what are we capable of solving for? We're capable of solving for the distance from the center pressure to the 0, 0. This distance is your YCP, right? So you have this entire distance, but you just want to find this little guy. So what's the difference? It's going to be YCP minus 10 feet, okay, is going to be equal to this little distance. So D is going to be YCP minus 10 feet. Okay? Now we have the ability to solve for D to get P. So if we rearrange this equation a little bit, it's going to be FD divided by 6 feet is equal to that force acting at the bottom of the gate. So let's write that over here because I'm going to need that equation. FD over 6 feet is equal to the force. Okay, just deleted some things to make some space, so let's move on. Okay, so we're trying to solve for our force due to a hydrostatic pressure and this distance D here, which D is equal to the YCP minus 10 feet. So we'll also need to find YCP. So find F and YCP. Well, the force is going to be equal to gamma H bar A or gamma Y bar sine alpha A. It really doesn't matter which version you use, H bar or Y bar. It really doesn't matter because this is your H bar, right? which is also going to be your y bar multiplied by your sine 60 degrees. So it doesn't matter. So just to kind of go back to where you get your specific weight, well, there's no information provided about specific weight, right? There's no temperature or anything. So we just assume that we're at standard, okay? So our standard specific weight is equal to what? In these units, 62.4 pound force per foot cubed. So the force is going to be 62.4 pound force per foot cubed multiplied by y bar, which y bar is 13 feet, multiplied by sine 60 degrees multiplied by the area, where the area is going to be 6 feet multiplied by 4 feet, which is going to give us 24 feet squared. Okay? So one thing I want to make sure you guys make a note of is to make sure that your calculator is in degrees when you plug in the sign. Just to make sure, double check. So the answer is going to be approximately 16,860.48 pound force. So let's check our units here. So we have feet cubed in the denominator, and then we have feet cubed here in the numerator, so then we end up with pound force. So this is going to be our answer for the hydrostatic force. So check, we got this. So now let's solve for YCP. So F is 1686048 pound force. Okay, so now let's try to solve for our YCP. So YCP is going to be your I XC over Y bar A plus your Y bar. Okay, well, your I XC is going to be 1 over 12 BA cubed. So again, don't get tripped up by that picture in the diagram, because if you go back to that picture, so looking at that here, okay. Do you see how the diagram, it shows the x-axis being much longer than the y-axis, but in this case, the x-axis is shorter? This picture is just meant to show you kind of the dimensions, right? Which axis corresponds to which letter. So B is always X and A is always Y. Don't look at the size of the rectangle. That's going to trip you up. So again, it's going to be B corresponds to the X, your A corresponds to the Y width. So B is going to be 4 feet and A is going to be 6 feet. So I XC is 1 over 12 B, 4 feet multiplied by A, 6 feet quantity cubed. Now do you see how this could be very dangerous? Because if you mix these numbers up, you're cubing the wrong number. So IXC is going to be 72 feet to the 4th power. So if we plug that into our equation, YCP is equal to 72 feet to the 4th divided by Y bar, which again, Y bar is going to be 13 feet, multiplied by the area, which is 24 feet squared, plus 13 feet, okay? Again, I want you to take a look at this. Do you remember the definition of the center of pressure? The center of pressure is always going to be below your centroid. You know that because of this equation. You're adding this distance to this distance, which this distance is your centroid, right? So this is YCP is always going to be greater than Y bar, just from this equation, okay? Just wanted to mention that again. So YCP is going to be 13.23 feet. Check your units, right? This is feet cubed, and this is feet to the fourth, so the product is going to be foot. Foot plus a foot, you have dimensional homogeneity. Okay, so now we have our YCP is 13.23. Okay, so YCP is 13.23 feet. So we go back to our balance, right? Our sum of moments is 0. We found that F multiplied by D divided by 6 feet will give us P. So F is 16860.48 pound force multiplied by the distance, where that distance D is equal to your YCP minus 10 feet, right? YCP is 13.23 minus 10 feet divided by 6 feet. And that's going to be the force P. So the answer for the force acting at the bottom of the gate is going to be 9,076.3 pound force. If you have any questions regarding this lecture material, I encourage you to email me at my Cal State LA email address, slope188 at calstatela.edu. And again, it has to come from your Cal State LA email address. So shoot me an email if you have any questions regarding this lecture.